Hello and welcome back to Steam It with Steve. Today we're going to do a little bit of an interesting deviation again. What we're going to do is we're going to look at the history of the different programming languages as they've come along. Now, this gives you some insights into why different decisions have been made along the way, and it helps understand how Python sort of works and also how pseudocode works as well, and where some of the influences happen there. So let's jump on in. This is a real quick little map that I found, which is pretty cool. Shows you sort of the general journey that we've had. You should see some pretty big languages in there that probably stand out. So something like C, for example, back in 71, C++. You got Python early 90s, Java's there. JavaScript's also something popular in C#. We're going to have a look at all these languages so that you can see how decisions were made along the way and why they were done the way they were. So what we're going to cover today, and this is going to be over 2 separate lessons, is the history of programming languages, how FORTRAN works with a little example, ALGOL, then COBOL, then Lisp, then BASIC, then Pascal, and then a C example, and finally at the end a Java example. So this will just give you a little bit of a flavor of each of the different languages. You're not expected to know how to code them, you're just expected to sort of have a play around with them and see what they do. There's a cool little video here. I put a link down in the bio that goes through the history. Have a look at that before you sort of jump into where I'm at now. So while creating the code, you're not expected to fully understand it. You're only expected to appreciate it. That's the important part here. So the first one, FORTRAN, is one of the sort of older ones, made by IBM way back in the day. This is what it looks like. If you look at sort of the original stuff. So you can see some things that might look familiar. So for example, in nested pseudocode, if, then, else, and then end if, you can see that sort of pattern. You've got write, and you've got the variables being stored. You've got then continue, which branches out things. You've got the goto function. So those that have done any sort of assembly machine level language, you can see that that's a little bit lower. So it's a lot more built for the actual computer. So it was created in 1953 by John Backus, who developed EB&F diagrams, which if you continue studying computer science, you'll definitely come across those. And it was built for IBM 704. It was programmed on punch cards. So you could actually program it on those punch cards, which is pretty cool. And it introduced statements. So having those lines of code just to make it a bit easier for a human to read and understand what was happening. You can also see the lines of the code as well here on the left. And then the goto statements are going to these little identifiers here. So goto 7 goes down to that part there. Also introduced if statements and then the goto statements, which allowed you to jump around on the screen. You then also had a loop, which was done by using the do loop. And then you had the ability to read and also write files. So for those that don't know what a punch card actually looks like, this is what one would look like. So you would have to go through, work out where your code needed to go, and then have a little clipper and then clip in those different bits. And they are literally bits. So where you clicked that, that is literally a showcase of the whole memory that's occurring at the moment. It's pretty cool. So what we're going to do is we're going to build a very basic FORTRAN. So what this does is checks the triangle, and what we're going to have a go at is just to see some of the different features inside this language compared to what we're used to when we've dealt with Python. I found an online compiler, which is pretty cool. So basically we'll click on that and then try and build this triangle to check to see if it is a triangle and what type of triangle it is, if it is a triangle. So is it equilateral, isosceles, and then scale in. So just pause the video, have a go, type that code, go to that website, and we'll go through it. Cool. So here's the compiler here. Just gonna make that a little bit bigger so you can see it at home. Let's go. All that and just build my program. So we're gonna go program. That's a keyword. Notice that it was all in capitals, which might look familiar if you've done the nested pseudocode. And we call it triangle. We're then going to go implicit. We've got an indent as well, sorry. Implicit, none. Then we're going to have the logical. And we call that L1, L2. Oh, that didn't go on the new line. Sorry about that. Enter again. We have an integer, side 1, side 2, and then side 3. We're then going to print out into the console. So this is an output. Type in 3 sides. Close the quotation marks. Then we want to read, and you want someone to type in the sides. So this is literally input. Side 1, side 2, and then side 3. Then we've got an if statement. So if 2 times the max, side 1, side 2, side 3, so it finds the maximum out of those 3 different inputs that you put in. And then this is where it's a little bit cool, GE, which means greater than or equal to. So that's greater than equal to. I've got a bracket there, sorry. So side 1. Is greater than equal to side 1 plus side 2, side 3. Close the bracket, and then, so that's like the snaky bite in Python. Then we're going to print out, and notice that it uses the asterisk to signify that there's an output or an input, not a triangle. Else. L1 is equal to side 1. So we're going to assign this. So the logical operator, which is a Boolean operator, is equal to side 2. L2 is going to check to see if side 2 is equal to side 3. If L1 dot and L2, then print out star. This thing here is going to be equilateral. Else if L1 dot or L2 those are the logical operators dot or dot side 1 dot equals side 3, then print star isosceles. Monkey does the highest and at the top. Isosceles. Else print star scaling. Then we got to end the ifs. Exactly the same as nested pseudocode. End this if. End this if. End program. Final. Run that. Type in the 3 sides. So we're going to go, let's go 4, 4, 4. Boom. And then worked out it was equilateral. Run it again. We'll go 3, 6, and that's not a triangle because it's too big. Then we might go 12, 12, 6, and then that's isosceles. There's some really cool stuff that you can sort of do here, and that works it out. Now, some interesting insights here, if we look at it carefully. Some things that should stand out is we didn't have to go through and find the logical operator or the Boolean condition for when each side was equal. So we didn't include this one. So we didn't do L3. Now you might be thinking, oh, that was a bit of a typo, but that was actually intentional. So because remember, when we're dealing with this language, memory was important. So you had to be as efficient as possible. So because L1 was used twice, that's why it was stored inside of memory. If it was only used once, you would just call it. The other thing that's quite interesting is it doesn't have an elif statement. So there are no match or switch statements. So you had to go through and do a separate if statement every single time and have this nested sort of pattern that would occur. And the other thing that was kind of interesting was the dots. So anytime an equal, you're trying to see if something was equal or greater than or and or, you needed to put a dot on either side to signify that was different. One other thing that I found was interesting, the else didn't need a snaky bite at the end. So it didn't need to say then, it just had to say else. So the then was pairing with that, which is kind of cool. So hopefully that gave you some insights into FORTRAN, which gave you a little program and something a bit cool and a little bit different. The next one we're going to play around with is ALGOL. So this comes along in the next bit, which evolved a little bit further. And what we found with ALGOL became a little bit easier to read. So you should be able to read that and go, oh, that looks not as intense. So it was created in 1958, introduced code blocks and pairings. So it had begin and end as well. Started an imperative programming language. So imperative means changing the state of the computer, which then had for loops as well. So you can see a little for loop there with the to statement. Gave the building blocks of most programming languages, so Python, C, and Java came from this. So some things, if we look here quickly, you can see that it has a variable, but you have to put let out the front to signify that that's the variable. You have a for loop. So the for loop looks very similar to nested pseudocode. So for I is equal to 1 to n. Then it has a do statement afterwards, which is a little bit different. And this is, sorry, for a bubble sort, for those that have done those before. Then you've got your if statement. So if this is true, do, and then it's going to have this part in here. And then it also had comments as well. So exclamation mark meant a comment to sort of block that bit out, which is kind of cool. So ALGOL was actually stored on tape, which looks like this. So you can see the little dots in the tape to work out whether or not it was stored, which was pretty cool. So a little bit different as well. So we're going to build a Roman number decimal converter, and what we're going to do is play around with this. We're going to have a structure with an array. So just pause the video, have a go at building that code with this online compiler. Cool. So if we open that up, we've got ALGOL compiler, and we're good to go. So to start, we're going to go begin. Conversion. This is a description of what's happening. Decimal to Roman notation. OP Roman is equal to an int number. Let's typecast it for a string, colon. Then we're going to begin. So begin int n colon dash number, comma, string sum, comma, and then we're going to have a list or an array. So we're going to go square brackets, struct, bracket space, int value, string r, brackets, table equals, here we go. So we've got all the different definitions. So 1000 is the same as an M. And then we've got a special case which is 900. Same as CN. Using single quotes, sorry. Need to change that. There we go. M. N. Next one. 500. B. 400. CD. Change these back. Double quotes, sorry, here, that was my bad. Just forgot single quotes used for if it's a single character. That's one that works with this language, so you need to use double quotes. Then we're going to go to the next one. So we've got 100. And we've got a century there, so that's what the C is for. Then we've got 90, which is 10 for the century. And we've got 50, which is an L. Is the L. Then what have we got? 40. Which then gives us XL. Then we've got 10. Mish, isn't it? Gives us X. And then what we've got here is a 9. Which gives us IX. Or 1 before 10. And then we've got a 5. There's one, sorry, just V. Then we have a 4. It's IV. And then we have a 1, which is the same as I. Put that on a new line as well, so it makes it a bit clearer. Cool, so that's the struct there, and because we've written a statement, we need to put a semicolon at the end. Now we've got a for loop, so we're going to go for I UP 8. Let's see what it actually says. So it's going a little bit here. So UPB table. Table. Do int b equal to a value of table at position I, string r is equal to r of table at position I, semicolon. While b is less than or equal to n, do sum plus snaky bite minus r n minus colon equals, that's right, yep, v, and then old or odo, the do and then odo, because that's all done, and you odo, which if you hopefully picked up is do backwards. Then you do sum, and we want to end the original statement from the beginning. Oh, so that's that operation. Now we're going to do the operation of the other side, which is decimal. So decimal is equal to a string has been inputted of text, then an int. So it's the other way around now. So instead of int, straight away the int is coming through. Then if ELEMS text is equal to 0, then it becomes just 0. Text is entered as 0, you get 0. Else, now going to do another operation. So ABS char s int, and then case int p semicolon void char in string s comma p comma IV XLCDM XLCDM. So we put in all the different characters that can be inputted. And P. So that's the option. In 1, 5, 10, 50, 100, 500, 1,000. Exact. And int b, comma, max b, colon, equals 0. Max b. Or p to UPB text, which is what we can't type it for. So UPB text. They then want to do if v colon equals the absolute value text, G, square brackets, greater, that's V, then that's P, colon, equals P, max V, colon, equals V, and then we do a reverse V, which means a reverse if, means the end, so that's the pairing, and then ode, there, and then max V minus the decimal x square brackets colon max P minus 1 square bracket plus decimal x max P 1 colon square brackets then we end the if statement from the original one. So we go phi, and then we can then print out and test these operations. So we're going to go print Roman 1968 brackets colon, and that's the same as XCML XBIII hash, and then we're going to try and print out decimal, and this time we're going to type in the string. I'm going to go XIII brackets hash, and that should be 2013. Sorry. What a mission. Awesome. So let's run that and see. Hopefully it works. So invalid character on line 11. So I didn't do that bit here right. So line 11. Should we do some, not dumb? That's my bad. See, the compiler tells you the answer. Invalid operator there, so plus just R. Sun plus snaky byte equals R and minus equals. So these are operators that are occurring. This is like the plus equals, and then this is the minus equals. Check begin, that matching end. Oh, sorry. Write down the end here. My end. Number 8. So for I. Line 3, begin, and colon, assignment, sorry, we'll get there eventually. Line 27. Missing is int v, max v, what am I missing? Let's look above it. Isaac, yep. Beneath it. There's a 4. Syntax error, so probably a missing or erroneous separator nearby. So if we go down into 27, Isaac definitely has a comma, in statement 1.5, and so on. Int v, max v, colon equals 0. Oops, we forgot a comma. There we go. And then our 10 v equals, oops, so I put a space in there, which is not so ideal. And it's the whole point I'm doing this is so that you can see it's not so easy without the compiler. And there we go. So it was able to convert that one, which is pretty cool. And then it was able to convert this one as well. So I got the 2013. Cool. So hopefully that's giving you some insight with our ALGOL. It was a lot more intense. What you should see is you've got the begin, then you've got operation Roman. So this is what Roman will be executing here. And then it needs to equal an integer number. which will eventually then spit out a string. So this is telling you what the data type is that it should be eventually. You then go begin int n is equal to a number, and then string is equal to the sum because it's going to end at the end each of the characters. It's then built this table that's got a pairing of a value with a string. So this is like an original dictionary, believe it or not. So you've got the key and then the output, key, the output, key, the output, and so on. And then basically it goes for I to U, the up B table, do int V, value of the table I, string R of the table, and then while V is less than or equal to N, sum the value of adding on R and then minusing that value away each time. So what happens here effectively is it takes away that value each time until it can't do it anymore. So it goes through each table and tries to take away 1,000 each time, and then each time it takes away 1,000, it appends on front the M, which is pretty cool. Then we've got, and then interesting structure here is you got the do and then the ode, and the do and the ode, and then the sum at the end, and then end. This one for the decimal is a little bit different. So decimal is you input a text string, which is going to be the Roman numerals, and then it outputs an integer. And then if the text is equal to 0, you just return a 0. Otherwise, you're going to go through the process in reverse. So you've got these characters here, and it's basically going to append those on as you go. So it starts with in reverse, and then puts the string together based off these values, connecting it with this. So this is how it's going through, and then it's checking to see if that's greater than the max value, and then it keeps adding that on, and then you can see the pairing there as well, which is pretty cool. So that's our ALGOL is 68, which is pretty intense. Hopefully that gave you some insights though. One of the ones that I take away from that is the if and then the fee. So that's a way that they did pairing back then, which was pretty cool. And then also the dictionary in the center. The next one that we want to cover then is COBOL. So COBOL is a little bit different. If you've ever seen the Terminator, it's actually the code that they used when he was looking around in his vision. So the way COBOL looks, basically you have these words, and the whole idea behind it was meant to be a bit more easy to read, so more business language. So it's sort of like the original pseudocode. So you've got add 1 to X, and then add 1, A, B to X, rounded, Y, Z, rounded, and then add A, B to C, on size error, display the error, and the add. Then add A to B, not size error, display no error, and then no error. So it becomes a little bit more English-like. So it was created in 1959, uses English-like syntax. So X is greater than Y. So instead of writing the symbol, you would write the word, which some people liked, some people were not so fans for. And then it had 4 basic lexical terms. So the lexical terms were that it had words, it had literals, which were the numbers, and then it had strings, so which were picture characters, and then it had separators to connect the things together. So lexical terms means the syntax or the structure that it had behind the scenes. There was a nice little bit of code that you can see. So there's the procedure, there's the main line, and then it has a bit of color that matches the different things to show when strings occur, when numbers and literals occur, and so on. So we're going to make a real simple COBOL example now, which is called identification division. And then basically it's going to see whether or not 2 numbers are greater than or equal. So let's open up that compiler, pause the video, and have a go and see if you can build that yourselves. Alrighty, here we go. So we're going to go identification division dot program dash ID dot hello dot data division dot working storage section dot then 01 ws dash num1 pick 9. So this is going to be picture characters, 9 length I'm guessing, and then 01 We're then going to also do ws dash num2 pick 9 bracket 9 dot, and now we've got another procedure. So we're going to go procedure, which is like a function, and we're going to call that division. So we've defined what the variables were first. That's what the data division did. And now we're going to define the function. So we're going to go a000 first parameter dot move 25 to memory at ws dash num1. Then we're going to move 35 to ws dash num2. Awesome. Go. Then if ws dash num1 is greater than or equal to ws dash num2, then display ws dash num1 is greater than ws dash num2. Else display ws dash num1 is less than ws dash num2. End dash if dot and then stop run. Let's get that execute. Oh, so then that's gone through, had two different variables that you've created, num1 and num2. Check to see what they equal. So you've assigned different values, and then it's gone off and worked it out. So if I put 44 in there now, it should swap the code and now say greater than. Now obviously there's a way that you can break this code. If I go 35, it will then go off and execute the else statement. If statement, oh sorry, greater than or equal. So no, sorry, my bad. It's got a way of checking it, but that's not actually true. So it should say is greater than or equal to. Oh. So some conclusion questions from today. Hopefully you picked up some things. So how does the understanding the evolution of these programming languages help you with learning new languages and seeing the legacy items that you could see? Which language did you find the most challenging? For me today, ALGOL wasn't so good, but that's all right. That's part of the journey of being a good programmer, is leaning into this and trusting the compiler to go through and unpackage what has to happen. And how do you think these languages have helped influence the modern language? So there is a little Kahoot that's attached. Highly advise having a play with that now, because it links directly to those languages that we've covered. So that's it from me. Hopefully you've learned something along the way. This is a bit of fun. These are cool little activities. This is sort of a bit of a nostalgia factor to see how these languages work, and then hopefully you might get some links to how Python works, and then also how pseudocode works. If you've enjoyed this video, please give us a like and subscribe, as it does help with the YouTube algorithm. And yeah, really appreciate all of the support that we're getting from this. So if you have any questions, please pop them down below, and see you next time on Steam It with Steve. Adios.